Okay, so there's this great demonstration, right, where I twirl a bucket of water over my head, right, and the water stays in the bucket. And the reason why that happens is that, remember, centripetal acceleration is toward the center. Okay, so at all points here on this circle, we're accelerating toward the center. Okay, and then at the top, basically, if the water is going to stay in the bucket, we want that acceleration to be greater than, or possibly could be equal to, I suppose, if you want to live dangerously, the acceleration of gravity. And the way that works is this: if I've got some thing, like just my hand or something like that, and I've got some object like that, if I accelerate this down, if that acceleration is greater than or equal to 9.8, right, then that object, either my hand's just going to keep up with it, or if it's greater than 9.8, my hand's going to have to push on that object straight down to make it accelerate down faster than gravity, because gravity is as fast as it will accelerate due to gravity, right? The acceleration of gravity is the fastest it will accelerate due to gravity, okay? So if at the top here I'm accelerating down, my centripetal acceleration will be down, okay? If at the top it's bigger than gravity, then the water will stay in the bucket because I'm accelerating the darn thing down, right? I've given it some inverted G force, okay? So this kind of problem looks something like this, okay? What is my minimum speed on the top? If the radius is 1.12 meters, what's the minimum speed I can have so that the cup doesn't fall off, so that the riders don't fall off the ride, the water doesn't come out of the bucket, all of this stuff, right? And all we do is we just use centripetal acceleration. We set the centripetal acceleration to 9.8. That'll give us the minimum speed, right? And so I'm going to use this formula. AC is v squared over r, because we're looking for speed. Say 9.8 is v squared divided by 1.12, and then we just solve for v, right? So the v is going to be 1.12 times 9.8. Then I'm going to take the square root of that, and I get 3.31. Okay, so if I'm going 3.31, at the top, the water will almost fall out, but not quite. Okay, if I go faster than 3.31, then at the top, I'm actually accelerating that thing down faster than 9.8. And it's just weird, right? Because we're going in a circle. It doesn't seem like it's accelerating down, but it is. Okay, so if it's faster than 3.31, I'd actually accelerate that thing down faster than 9.8 at the top, and the water would stay in there. To be sure, when I show you that demonstration, I'm probably pulling like 2 Gs or something like that at the top, so that the cup is firmly rooted against the plate, right? Okay. Anyway, that's how you solve those. If it's the minimum speed, right, just set the centripetal acceleration equal to 9.8. Yeah.